Right. So we've got a work example for a proof by induction. This is a fairly tricky one, really, because it kind of incorporates um, a rather obscure step. Let's have a look. Prove by induction that for all positive integers n, this f of n equals 2 to the power of 3n plus 1 plus 3 into 5 to the power of 2n plus 1 is divisible by 17. Right, so well, let's so look, base case, then also we'll do establish that it's true for n equals 1. Assume that it's true for f for n. And then if we can prove that it's also true for n plus 1, then so f of n being true implies f of n plus 1 is true. Then of course it's then true for all positive integers. Because that that proves that f of 2 is true and then f of 3 and so on. So here we go, the base case. So all we have to do here is substitute n equals 1 in this expression here. Um, and when we work that out, it actually comes to 391, which indeed is a multiple of 17. So, okay, so f of 1 is divisible by 17, so it's true for n equals 1. And then we make the assumption, this is the assumptive stage. We assume that f of n is divisible by 17. Now, there's kind of one or two variants on how we do this, but this for this particular one, what I'm going to do is if I can show that the difference of f of n plus 1 minus f of n is divisible by 17, then because this is assumed to be divisible by 17, if this whole thing is divisible by 17, then it means that this part is divisible by 17. All right. So in the case where you've got this kind of thing divisible by 17 or some property like that, then this is the sort of thing that you might be wanting to do. Right now, the sort of trick here really is that what we're going to try and do is we're going to simplify this expression, um, and we can actually show that it looks like this again. So this is a kind of a not untypical pattern, but to be quite honest, it's not that easy to spot. Let's have a look. All right, so if we actually look at this, I mean, obviously this part here is just the same expression as we've got here, but with n plus 1 substituted in for n. So that's going to give us, it is going to give us not what I've got there, but an actual 3n plus 4. All right. Okay, so yeah, so that's just substituting n plus 1 in for the 3. So we've got 3 into n plus 1, which is 3n plus 4, um, plus 3 into 5 to the power of 2 into n plus 1, which gives us 2n plus 3. Okay, that's what we got there. So that's the n plus 1. That's the n plus 1 version of 2n plus 1. And then minus this expression, basically f of n. Talk about that. And if we were to now group those base 2 and the base 5 terms, it's going to look like that. Now, if we factorize 2 to the power of 3n plus 1 out of that, we're going to get that. Yeah, so we take 2 to the power of 3n plus 1 out of that, we're left with 2 cubed, 8. And then we'll do a similar thing over here. Take out 3 times 5 to the power of 2n plus 1, and that's going to leave us with 5 squared. Yeah, that out of there, and that's going to leave us with 5 squared, 25 minus the original term, which is 1. Right, so that's all 24. So this is 7 here, and that's 24. So if we rewrite that, we've got that, and then this times 7 plus 17. Okay, so at this point, what we're going to do is we're going to um, so that's kind of the crucial thing almost, actually spotting. Well, spotting that 24 is equal to 7 plus 17 doesn't sound earth-shatteringly difficult, does it? But it is the trick that sort of unlocks this whole thing. So if we were to group that and then this part here into this term, then we've got 17 lots of this left over here. Right. Okay, so this is our f of n as per there. Okay, and we know that's by our assumption is divisible by 17. So we'll just write it's 17 times k. And then obviously we've kind of factorized 17 out of that. All right, so this difference here is going to be that which is divisible by 17 plus that which is divisible by 17. So then the whole thing is divisible by 17. So in other words, the fact that if it's divisible by 17, we've kind of used that assumption here, haven't we, when when we've turned that into 17. Okay. So the fact that that is divisible by 17 by our assumption implies that f of n plus 1 is divisible by 17. And so being true for n equals 1 and also being true for n implies it's true for n plus 1, then it is true for all n, which are positive whole numbers. So that is basically it. So I think the takeaway from that really is this idea of kind of stripping out this thing. You might not need to do it, if we can actually look at this whole thing and somehow work out that it's divisible by 17, then that is fine. But there's not completely obvious from that stage there, is it? Okay, so hopefully that has been useful, and thanks for watching.